Hopefully this will make sense. It'll probably seem a little bit confusing initially, just because it's confusing stuff a little bit, but I'm going to try and tie it in. I wish we could do there's some really fun demonstrations. I'll talk more about them tomorrow that I normally do, that I can't do because I don't have a camera that can photograph stuff in the dark. So at any rate, here's what we're doing. We're going to finish up talking about our models of the atom with what we, for almost the last 100 years, think is the explanation for how matter's put together. And then there's a review for you to do. Ed Puzzle. So this is the first part of section 1 in chapter 5. As usual, I'm going to skip around. Tomorrow we'll talk about section 3, but you guys know how I am. I move around the book like a crazy person. So hope you're doing well. Hope everything is going as well as possible for you. This, again, I'm going to recommend that you take notes. I didn't make an outline for you today. My apologies. But I probably will for tomorrow's lecture. So models of the atom. You actually, let me go back to this. You actually have a worksheet from October, the middle of October, that we used. This is page 2 of the atomic theory history. You might recall we talked about Robert Millikan, the American chemist who figured out the charge on an electron. And then we left off talking about Ernest Rutherford's nuclear model. The idea that almost all of the mass of the atoms concentrated in the nucleus, and the electrons are out here somewhere. We don't know where, and that's where we're going. So I'm going to mention Niels Bohr. James Chadwick in 1932 is credited with discovering the neutron, and then these three gentlemen are, well, Bohr and these three gentlemen are the people we're going to focus on today. I'm not going to go into this this year. I will show you an image of the standard model. You can look it up if you're interested. We'll talk about that in the PowerPoint. But this is back from October. It's in your classwork feed. If you want to reference it, again, you don't have to use it. We just normally would use it in the classroom. I will give you a copy. Take notes. All right, so models are important in science. They are used to help us understand things. And so there's 3 main kinds of models. First one is a physical model like this, a model of an airplane. Excuse me. And this airplane's in some sort of a wind tunnel situation to see how air moves around it and how it would behave in air currents. So you might have made model airplanes, you might have made model ships. Physical models are great. You probably made a model of the cell in biology. So you can take something small and scale it up to big. You take something big and scale it down to small. That's a physical model. Another kind of model is what they use on meteorologists use all the time to talk about weather and make predictions. So when they're trying to predict where a hurricane is going to go, they take into account past data on temperatures, humidity, wind patterns, ocean temperatures, atmospheric temperatures, all different things. And then they push all those numbers into some sort of algorithm through a computer, and they make predictions for the path. Sometimes it works, sometimes it doesn't, okay? But that's how they predict when it's going to rain and all sorts of things. So mathematical models are super important in science as well. We're going to focus more on a conceptual model, like taking something you already understand and projecting it to something you don't understand yet. And hopefully that'll make sense here in a few minutes. All right, so what models do we have? We've had several. Dalton at the early 1800s put forth in modern time the first idea that matter's made of some littlest bit. At some point, you chop it up, you can't get any smaller, okay? And of course, it's solid. About 100 years after that, J.J. Thomson discovered the electron. He was using cathode ray tubes. Different gases, different metals in the electrodes, same results. These little charged, negatively charged bits are coming off of them. He discovered the first subatomic particle. Every kind of atom has these things, okay? So that's cool. A few years later, Ernest Rutherford puts forth his concept that, okay, we got these little negative bit things, but matter's not solid, okay? Unless you're at the very, 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 very center, super small volume, positively charged nucleus. So he's credited with a nuclear atom. This is not to scale. Okay, it's not even close to scale. It should be huge. If the nucleus was the size of that green dot on your screen, the electrons, closest electrons, would be thousands of meters away. Okay, I mean, it's really, truly most of matter, most of everything is nothing. It's so nuts. And Rutherford didn't really, he was working with radioactivity and radioactive substances. Remember, he coined alpha and beta, shooting those alpha particles at gold foil. He found the nucleus, but the question, of course, was where the heck are the electrons? That's where his graduate student, who we're going to talk about today, Niels Bohr, comes in. But first, let's talk about some other problems. First of all, we don't know where the electrons are. And second of all, there's some other interesting phenomena that Rutherford's model doesn't really explain. And one of those is the fact that when you heat objects, they change color. I'm not talking about burning things. I'm talking about like heating a horseshoe or something. Now, some of you probably have electric stoves, and you've seen the coils, change color. Probably all have a toaster or toaster oven and seen the wires change color. The resistivity of the metal causes friction, which causes heat, which causes the color to change. Why is that? Well, weirdly, most everybody goes, well, hot is red, right? Red, hot, oh my gosh, that's the worst. Well, actually, that's not the case. This yellow area is actually hotter than the red and orange area on here. Okay? It's actually got more energy. These particles are moving faster than the red hot area. And certainly, of course, on a horseshoe, any part of that heated horseshoe is going to damage you, the living thing, but the highest temperature is here. And astronomers actually use that phenomenon of color and temperature to determine the surface temperature of stars. And I'll probably talk more about that later too. Another problem with Rutherford's experiment or explanation of the atom is, okay, so you got these positive nuclei, massive, especially for something like gold. You got these electron things. Why don't they all crash into the nucleus? They should be attracted to each other. Opposites attract. That rotating electron everything should collapse on itself. And of course it doesn't. So what the heck? Another interesting little tidbit here for classical mechanics is that if you're going to have an object in a circular path, you're going to have to constantly be inputting energy to keep it on that path. Natural tendency, right? Newton's laws, objects are going to keep on doing what they're already doing. And if you've ever swung anything at the end of a rope, like over your head, you let it go, pew, off it goes in a straight line. That's what the electrons should do, but they don't. So what the heck? Well, Niels Bohr said, okay, we got those electron things, they're outside the nucleus. They have their own fixed orbits. And so the term orbital came about. And of course, probably most of you are making the leap mentally, this conceptual leap that the center of the atom, the nucleus, is like the center of our solar system, the sun. Almost all the mass is in the sun that exists in our solar system. Almost all the mass of the atom is in the nucleus. We've got planets going around the sun, pulled in by gravity, of course. Electrons are pulled in to the nucleus in the same way. Every planet has its own orbit. Every electron has its own orbit. Sounds really great. It was just like, oh, unification of the universe. We got this parallel from the gigantic universe, our solar system and the universe, down to this tiniest bit of matter called an atom. It really has appeal. It really makes some sense. It's not quite right. Close, but not quite right. It worked perfectly for hydrogen, 1 proton, 1 electron. Didn't work for bigger atoms. But the principle, the concept's really close to the truth. So again, positive nucleus at the center, negative electrons orbiting around. There's not a fixed path. You can't ever predict exactly where an electron is. We'll get to that. And then this diagram will make sense in a minute. You can give electrons extra energy, give them a little kick, and they'll change energy levels. They'll change positions, distances from the nucleus. And that's where Bohr came up with this idea. And hopefully I can make sense of that for you here in just a sec. So another phenomenon that had been known about for a couple hundred years, probably before, maybe longer. It was, you know, Newton, Isaac Newton in the 1700s was doing stuff with light and prisms and proving that white light was really all colors of light by passing it through 2 different prisms. Some of you might know that story. At any rate, people knew that if you heated up elements and looked at them with something called a spectroscope, they gave off these colored lines. What the heck? Even colorless, odorless, invisible gases had these distinct line patterns. And those distinct line patterns are called spectral lines. The spectrum of each element is unique. Just like your fingerprints are unique, each element's spectra is unique to that element. And we can use it, spectroscopy, to identify, you know, what's in stars. We can use it to identify if there's water on the moon, because it works for compounds as well as elements. We can analyze foreign materials through spectroscopy as well. But we're just going to focus on gases and electrons right now. So how does it work? You've got gas in a container, a sealed tube, and they heat it up. You could use just a regular fire, or you could, which is, of course, could damage your tubing, but we use electricity now. And so you charge up those particles in there, pass the light through it, focus that light, pass it through a prism, and you get these distinct colored spectral lines. There's different styles of spectroscopes. We have a really old one in the department that's really cool to look at. I have a picture of it in tomorrow's presentation. And there's also some different boxes. If you were in Mr. Westfall's Earth Science class, you might remember the spectroscopy lab. You have little slides. They're pieces of plastic film that have, I don't know how many thousands of slits per centimeter. And that acts to refract the light. You've all seen rainbows. It's the same principle. Water droplets in the atmosphere after a rainstorm refract the light. The longer wavelength reds bend the most, the purples bend the least. It's the same idea, only instead of seeing a full rainbow when you look at a specific element, you only see certain colors. Turns out certain colors are related to certain energy, right? We've got a little hint of that on our electromagnetic spectrum information last week. Color is directly related to energy and wavelength of light. And somebody made that connection, and that somebody was Niels Bohr. So again, spectroscopes split the light into all of its different colors. How does that relate to the atom? Well, visualize an atom, just a little basic, flat, wrong-sized atom. And an electron. Here's a nice hydrogen atom, 1 proton, 1 electron. Electrons going around. If you give that electron a little kick, a little bit of energy, boop, you bump it up to the next energy level. You can think of this like stairs, okay? You're at a certain level, you put some muscular energy, which came from chemical energy in your food, which we can go through all the different pathways, but you can take a step up to the next level. Okay, so if you get a little push, you can go to the next level. But the thing with electrons is they don't stay at that higher level for long. They will fall back down to their ground state. The energy that was absorbed is then emitted back into the environment, sometimes in the portion of the spectrum that you can see with your eyeballs. Sometimes you need a special instrument to see what's in the ultraviolet or infrared region. But the energy that goes in comes out. If you're lucky, you get to see it. Okay, so again, ground state, incoming photon of energy excites the electron, bumps it up a level. That electron gives it back off, and light of some sort is released. In the case of hydrogen, there are these 4 different colored lines. So different scientists saw different patterns depending on whether they were looking at ultraviolet light, infrared radiation, or visible light. If the electron is at the 3rd energy level and goes down to the 2nd, it gives off the red light. If it's at that's visible to your eyeballs. If it's at the 4th energy level and drops 2 levels down to the 2nd, it gives off higher energy, blue-green. If it drops from 5 to 2, blue-violet. If it drops from 6 to 2, it gives off violet light, purple light. And that correlation in the hydrogen atom was worked out very neat and tidily by Niels Bohr. Unfortunately, like I said, it didn't work for bigger atoms, and there's more to the story. Okay, so we call these energy levels. So the little tiny black speck in the middle here is supposed to be the nucleus. The first circle is the 1st energy level, the 2nd energy level, 3rd, 4th, 5th, etc. Those energy level things correspond to layers on the periodic table. And I'm hoping by the end of next week to make that clear for you guys that there's this really cool, the periodic table is amazing. And if you understand it, which I hope I will help you too, it's really, really useful for figuring out about electrons. So I can still remember figuring it out and just like mind blowing. Okay, all right, so each energy level is different distance from the nucleus, kind of like layers on a cake or layers of sediment in the ground or whatever you want to talk about. You need more and more energy to move from one level to the next, just like walking upstairs. That's an easy one. And we call that amount of energy a quantum, a specific quantity, a specific amount you need to move. Okay, this is a really bizarre looking ladder. You should be kind of concerned here. It's really strange. And that's because the energy levels require different energy to reach, right? So try and make this parallel for you, and hopefully this concept will help you understand about electrons. Those energy levels, again, aren't evenly spaced. It takes a little bit less energy to get from one to the other after you get started. And this is important too, we'll talk about it later, you can put up enough energy to totally leave the ladder. Okay, so hang with me on this. All right, so if the ladder rungs correspond to energy levels, ground level is the green grass there. The nucleus is right under the ground, for example. Let's just say this is hydrogen and there's an electron right here, okay? I can give a little and bump it up to this from ground level to the next energy level. If you don't give it the right amount of energy, it won't get to that rung. So, true confessions, I've fallen upstairs, going upstairs. Probably some of you might have too. Didn't quite get enough energy to get up to the next step. Same thing. You can put lots and lots of energy in, but if it isn't this amount, you go back down. Okay? And you can climb to the next one and the next one and the next one, and you can fall all the way down. or you can fall from this step, or from this step, or from this step. It's like the electrons. This is another book's picture, again, of this weird, wonky staircase, really big first step, smaller second step, smaller, smaller, smaller. Same idea. Ground level, first energy, second energy, third. Okay, so that's where we left off, and it was pretty good. Bohr said we got to have a certain amount of energy for the electrons to transition. When they come back down, that's where these colors are coming from. Again, it didn't work for bigger atoms than hydrogen. So the three people on the bottom of that note sheet, first one is Louis de Broglie, a French physicist, obviously, in the early 20s, said that, you know, these electron things, these particles of matter, also have a movement like a wave, like energy. There's this interchangeability between matter and energy. So waves are the energy, particles are the matter. They call it wave-particle duality. So this whole way of moving with electrons is wave-like, which was weird. Light, of course, most of us would say is energy. However, it also behaves like matter, okay, and can knock matter off of things. Photoelectric effect. All right, so that's one. The second little piece was put up by Werner Heisenberg. He said you can't, he's also studying electrons, because that was a cool thing, right? What are we doing with these electron things? Where are they? He said if you're trying to find out where an electron is, you don't know, you can't know its exact velocity at the same instant. Okay, if anything you do to look at an electron, like shooting in the right size photon to see, quote unquote, an electron, you're going to change its path. You're going to change what it's doing. And so this shows a photon being struck or striking an electron. That photon then goes off on its merry way in a different direction from when it started, and the electron also goes off in a different direction than it was going. Anything you do, you can know one, you can know where it is, but then you change the velocity. You can know what its velocity is, but then you change its direction. Okay, that's Heisenberg's uncertainty principle. The analogy in her book is this really bizarre airplane. It has two propellers, some sort of experimental plane. I wish I had some explanation, but it doesn't matter. You've all seen plane propellers, I'm sure, before, or a boat engine propeller, same idea. You can see it spinning when it's going. You know there's propeller blades there, but you can't see the individual blades. Anything you do to see the individual blade is going to change the velocity of that propeller. Right? This slide isn't that important. I just want you to understand, obviously, when you're bombarded by light, it doesn't affect you. By photons, it doesn't change your velocity or position. However, something as small as an electron, it does. So this is a classic physics joke. You know, if you want to get out of a speeding ticket, throw the Heisenberg uncertainty principle at the officer. It won't work. Don't do it. Okay, and then in a quantum world, how can we be sure? Yeah, just silly physics jokes. Speaking of silly physics, here's Sheldon to share his take on Heisenberg. I just enjoy Big Bang Theory. I'm sure you guys know that by now.
That's just the way.
Yeah.
Other in one perfectly correct. Oh boy. What? I can't comment without violating our agreement that I not criticize your work. Then what was oh boy? Great restraint on my part. There's nothing wrong with the science here. Perhaps you mean a different thing than I do when you say science. Okay, how's that? You actually had it right in the first place. Once again, you've fallen for one of my classic pranks. Bazinga. Now, here's a peculiar email. The president of the university wants me to meet him at his office tomorrow morning at 8 a.m. Why? Doesn't say. Must be an emergency. Everyone at the university knows I eat breakfast at 8 and move my bowels at 8:20.
Yes, how did we live before Twitter? I guess you'll find out what it is in the morning.
That's 14 hours away. For the next 840 minutes, I'm effectively one of Heisenberg's particles. I know where I am, or I know how fast I'm going, but I can't know both. How am I supposed to carry on with this huge, annoying thing hovering over my head?
Yeah, I know the feeling.
So silly, silly, silly. Let's see, you wouldn't get the joke unless you knew science. Okay, so thanks to Schrodinger, we now have an explanation. Our book says 1926. Most of the books that I've seen put it later in the 20s, but Schrodinger worked out the math to explain the behavior of electrons in the hydrogen atom. And this awful equation, have no idea what to do with this. I don't know what any of this stuff is. I don't know. But thankfully, there's smart people in the universe that can figure it out for us. And his math worked not only for the hydrogen atom, but for larger atoms as well. And we now explain the atom as what's fondly called the quantum mechanical model, but more commonly called the electron cloud model. So most of us can visualize what a cloud is, of course, and in that region of space around something, around that the cloud might be around, their electrons are zippity-doo-dah around. They're not on a fixed path. There's no way to predict it. We can't know where it's going to be from 1 second to the next. We know where it should be most of the time, but no guarantees. Okay? So it gives us the allowed energies electrons will have and tells us the probability. So going back to probability again, you know, like flipping coins, 50-50. This is way better. 90% chance you'll find an electron in a certain region around the nucleus. And that is the electron cloud model. Obviously, that's a little bit harder to process than the orbiting planet around the sun kind of model. And so you can understand why, sure, the orbiting electron thing is hard to get rid of. We really don't know. We can't predict where it's going to be this month or next year. So in your book, it shows this red blob around the nucleus. It's a fuzzy area because the electrons could be anywhere. Notice it's darker closest to the nucleus because negative things want to be closer to positive things. So more of the time it's going to hang out close to the nucleus, but 90% of the time it's going to, it's going to be in this region. Could it be out of it? Yes. Okay, but most of the time it'll be in here. Physicists took that and ran with it in the 1900s, mid-1900s. We came up with what's called the Standard Model, and that's the stuff I was talking to you about, quarks and fundamental forces and all that, antimatter, dark matter, dark energy, all that stuff is the realm of physicists today. And we don't need to talk about that. You can do modern physics some other time. All right, again, electron cloud model tells us the probability of finding an electron in a certain volume. Turns out the clouds have certain shapes, and all of those shapes are mathematically provable. It's not any math that I can do, but it is provable with Schrodinger's math. Okay? Again, it's denser, more likely you are to find electrons closer to the nucleus. It's just another representation with a bullseye kind of thing. All right, so that ends our introduction to the modern model of the atom. I'm sure it is more than enough for one day for your brain.